Okay, so I'm starting the class today. So in today's class, we will be discussing the assignment 9 previous year questions and some theory. So here we will be discussing about the starting methods, and then we will also see the some theory on speed control, and then we will see the questions. So let us start with the starting method. So these are all pictures which I have taken from the search slides only. So let me explain what are these methods. So in starting methods, there are basically four categories. One is the direct online starting, then the reactor starting, auto transformer starting, and star delta starter. Okay. Now in the direct online starting, what you do is that suppose first of all, there are two things. One thing is that these are starting methods, and another thing is regarding the slip ring induction motor or the squirrel cage induction motor. Now, in the case of slip ring induction motor, so let me just write some things. So let us first discuss the slip ring induction motor. Okay. So slip ring induction motor, rotor resistance starting. So I will draw the slip ring induction motor. So let us say this is the stator of the slip ring induction motor, and then you have the rotor of the slip ring induction motor. Now, we have seen that in the slip ring induction motor, what you can do is that in the rotor circuit, so let me write, this is rotor, this is stator. So what you can do is that here in the slip ring induction motor, you can connect external some three-phase resistances, let us say. So they are together, you can vary them. Okay. So this is the thing. So here in slip ring induction motor, you can connect external resistance in slip ring induction motor. So in the equivalent circuit diagram, what you have is, so here you have R1, JX1, which is the stator side. This is R2 dash by S, JX2 dash, and then some R external which you have connected. Okay. So this is the R external. So first of all, in motors, what we want to do is that in motors, like why we want to have some starting methods. Okay. So in motors, okay, in the at the starting, the current drawn is very large, and it can damage the windings of the motor. Also, it causes voltage dip issue. Okay. Also, it causes voltage dip. So you will see that in induction motor, the starting current, so starting current is at least 8 to 10 times of the full load current. Okay. Is 8 to 10 times of full load current. So it is very large, right? Very large than the rated value. So what can happen is it can cause the first of all damage in the windings. Then another thing is that what will happen if suppose you in very in an industry some induction motor is running. So whenever that induction motor is starting, it will draw the huge current, and what will happen because of this huge current being drawn, there will be a voltage dip to the other loads which are connected. Right. So what will happen is that the for other loads it will be some under voltage conditions when the motor is starting. Now if the motor has to continuously start and run, then start and stop. So what will happen whenever the motor is starting, it will continuously draw huge current. So it will impact the efficiency of the other components which are connected in that phase. Okay. That is why what you have to do is you have need to have starting methods. Okay. So for slip ring induction motor, one method is to connect the rotor resistance in the rotor side. So what will happen to the starting current? So so let us say this is V phase. Okay. So what will be the current drawn? So let us say current drawn is I starting. Okay. So I start. So in this per phase diagram also, this is let us say V phase, and this is I start. So it will be V phase by root over of R1 plus R2 dash by S plus R external. Now S will be 1 at the starting, so let it be 1. So this will be R1 plus R2 dash plus R external square plus X1 plus X2 dash square. Okay. Then plus x1 plus x2 dash square. So we can see that by connecting the R external, you can restrict the starting current such that it does not damage the windings of the induction motor. Okay, but this is for the slip ring induction motor. Now what about the squirrel cage induction motor? In squirrel cage induction motor, you cannot connect the rotor circuit is not accessible to us, so we cannot connect any external resistance, right? So this is the slip ring induction motor external resistance method. Okay. So external resistance method in slip ring induction motor. Now we will see some general methods which you can apply to both the slip ring induction motor and squirrel cage induction motor. But this method is specific to slip ring induction motor. Okay. Now let us see those methods. So these are the methods which is called direct online starting, where you do not do anything. You just directly connect it to the rated voltage. That is called as direct online starting. Then there is something called as reactor starting. Then we will see auto transformer starting, and then star delta starter. Now in star delta starter, like what we do is initially under normal operation, your machine will be connected in delta. Okay, and it will be running. So stator of your machine, let us say this is squirrel cage induction motor. So rotor is like this in the form of cages, and here you have the stator of the induction machine. Now let us say in the normal operation, the induction machine will be running in delta connection. Now in starting, what you will do, you will make the connection such that it will be connected in star, okay, for starting, but under normal operation it will be brought back to delta. So star for starting. Okay, so star in the starting. So what happens is that you see, so this is the V phase here, right? But for the star connection, this voltage across one winding becomes V phase by root 3. So we can see that the voltage only becomes V phase by root 3 means that you can restrict the starting current, right? That is why it is connected in star. So that is why, because our machine under normal operation will be connected in delta. That is why for other methods also, like direct online starting, reactor starting, and auto transformer starting, we are assuming that the stator is connected in delta. Okay. So that we can compare because see, if I assume that with this connection to be star, and then we derive the torque and current expressions, then we cannot compare it with the star delta starter, right? But under normal operation the machine stator will be in delta. That is why what we are doing, we are assuming that our machine will be in under normal operation will be in delta connection, so that we can compare it with to the star delta starter method. Okay, so let me write here that under normal operation, it is assumed that stator is delta connected. Okay, so this is what we are doing, and why we are doing this is so that we can compare the star delta starter method with the other methods. So let us first discuss the direct online starting. Now in direct online starting, what you do is you directly connect it across the rated supply. So here you have your stator, you can see that. So let me use this. So here you can see that you have your stator which is delta connected, and because we are saying that okay, these methods are for both squirrel cage induction motor and slip ring induction motor. So here let us take the example of squirrel cage induction motor. Okay, so this is the connection. Now here what happens, so if you draw the per phase equivalent circuit diagram of this circuit, so what you have R1, X1, X2 dash and R2 dash by S, where S is equal to 1, right? Because this is at the starting. So this is R2 dash by S, where S is equal to 1. Okay, for starting. So this is the equivalent circuit diagram. So what will be the I starting? I starting will be nothing but the per phase voltage. Now per phase voltage is V rated with line to line voltage, and also for star connection the line to line voltage and phase voltage are same. So this becomes I starting current is V rated by ZC. Okay, so this is the I starting current in the winding of the delta connection, like in this winding. But what about the line current? Now we know that the relation between the line current of the delta connection and this winding current is that the line current is root 3 times of the winding current. So that is what is written here, that starting current in the line is root 3 times of the starting current in the winding. So what happens to the starting line current? It becomes root 3 times of V rated by ZC. Okay. And what about the starting torque? Because we are in the starting, what we are interested in? We are interested in what is the amount of current which is getting drawn and what is the starting torque, right? These are the two things which is of interest. So let us see what happens to the starting torque. So starting torque is air gap power if we neglect the mechanical losses. And what is the air gap power? It is, so we have seen that the air gap power, so air gap power is 3 I2 dash square R2 dash by S, but this is starting torque. So, so starting torque is this for slip equal to 1. So it will be proportional to this. So starting torque will be proportional to air gap power. Actually, starting torque exactly should be air gap power by 2 pi ns. But we are saying they should be proportional. Okay. So we are using a proportional signal, that starting torque is proportional to air gap power and starting torque is proportional to 3 I2 dash square R2 dash by S. So what is the I2 square? So I2 square is the current in the winding. So this is I starting winding square into R2 dash by S, where S is equal to 1. Okay. So this is the so this is your starting torque. Okay, so let it be here. We are not using this value. So just for now, you just neglect this. Okay, so this is the starting torque and this is the starting current. Now we will be comparing the starting torque and the starting current of various methods. Okay, so we know that in direct online starting, what will happen, because we have connected the rated voltage across the machine, so machine will draw huge current, and then there will be various issues, right? The winding can be, what you say, damaged and all that. That is why this direct online starting is used only for small machines. Okay, it is not used with large machines, because large machines will draw very large current, and it will affect the nearby, what you say, other equipments voltage. It will cause the voltage dip for the other equipments, right? So that is why this direct online starting is generally used for small machines, so it is not used for large machines. We are just derived it for the comparison sake. Okay, so this is the equation. Now we will see in other methods what happens to the starting current and starting torque. Okay, so this is the another method, which is the reactor starting. Now here what you do, along with the supply, you connect a three-phase reactances externally to the stator of this machine. So you can see that these are the three reactances. So we are saying that the reactances are put in such a way. So what will happen if you connect? So this voltage will get divided among this reactance and this winding of the this induction machine. So what will happen, that instead of having V rated, like earlier, whatever V rated supply which we were giving, that was whole V rated was coming across the induction machine. Now what will happen, whole V rated will not come, some portion of the V rated will come across the winding of the induction machine. So let us say it is X times of V rated. Okay, some percentage of V rated. So let us say this is X times. Now X can vary from 0 to 1. 0 means you have connected infinite, a very huge reactance. Okay, that we generally do not do. And X equal to 1 means there is zero reactance. Okay, so in, like, let us say, suppose you have connected the reactance in such a way, let us say for X equal to 0.5. So these reactances are connected such that the half of this V rated is dropped across this reactance, and other half of the V rated is coming across the induction machine. Okay, so like that, by connecting the value of reactance, you can control how much of the V rated is coming across the induction machine in this method. Okay, so here what will happen? So, so the starting current, so the starting line current. So first of all, starting phase current will be what? So starting in the current, in, so what is the equivalent circuit diagram? So it is like this. So you have R1, JX1, R2 dash, JX2 dash. R2 dash by S, but S is equal to 1. Okay, so R2 dash. Okay. Now here what you have XV rated. So what will be your I starting this winding current? So this I starting winding will be XV rated times of this equivalent impedance. So let us say this equivalent impedance is ZSC, because this is what we have taken in the earlier example also, right? So in the earlier question, in the earlier this direct online starting also, we have taken ZSC, so we are using ZSC. Okay, so here I starting winding was V rated by ZSC, but here now I starting winding has becomes X times of V rated by ZSC. Okay, and what about the line current? So line current will be root 3 times for the delta connection. The line current is root 3 times of the phase current. That is why there is a factor of root 3 X V rated by ZSC. Now, regarding the starting torque, so starting torque is proportional to, so starting torque is proportional to 3 times of I starting winding square into R2 dash by S, where S is 1. Okay, so it is proportional to 3 I starting winding square into R2 dash. So it is proportional to 3 I starting winding we have found here in this expression, which is X V rated by ZSC. So this is X V rated by ZSC whole square into R2 dash. So if we compare it with the direct online starting, then we can see that the starting line current becomes X times of the online starting current. Okay, so I starting line current due to this reactor starting is equal to I starting line current of direct online starting into X. So we can reduce the starting current by the factor of x, because remember x is a fraction between 0 to 1. So that is why we can reduce the starting current by using this reactor starting by x times of the direct online starting. But what happens in this process, if you see the starting torque of the reactor, it also reduces by x square times. Okay, so what happens is that you are able to limit this current, right? You are able to limit the starting current, but in that process what happens, your starting torque also gets reduced by x square time, which we do not want. Okay, this is the pros and cons of the starting method. Like what happens, you are able to reduce the starting current, but what happens, you lose the starting torque. Okay, the starting torque gets reduced. So let us see if we can overcome this in some other method, in some form. Okay, so we will go to now auto transformer starting. Now in the auto transformer starting, you can see that what we do, we connect the auto transformer, and from the auto transformer tappings, we take the uh, line connection to the induction machine stator. Okay, so here also what happens, by changing this tappings in this auto transformer, you can supply this V rated as X V rated across the stator of the induction machine, just like the previous method. So here also you get XV rated, but there is something else which you will see happens. Okay, so here also what happens, that I starting of the auto transformer is what, XV rated by ZSC. Here also, because voltage becomes X times of V rated, that is why XV rated by ZSC. And I starting line current drawn is root, but remember, I starting line current drawn here. Okay, here you can see here, not here. Here we have not reached here. Here it is root 3 times. Okay, so in this side, in the line connection of this delta winding, it is root 3 times of XV rated by ZSC. Okay, so but what happens to this current which is actually getting drawn from the supply? What we want is that the current drawn from the supply should be less, should be reduced. Okay, so let us find that. So how we can find it? You can find it by doing this VA balance. Okay, so for the auto transformer, what you can do, VA at the input should be equal to VA at the output. So VA at the VA at the input is how much? So it is root 3 times of V line to line V rated into this line current I starting line. So VA, so VA of transformer is written like root 3 times of V line to line I line, where V line to line is line to line voltage and I line is line current. Okay, so what we will do, VA at the input of this auto transformer should be equal to VA at the output of the auto transformer. So VA at the input is how much? It is root 3 times of, because here it is root 3 VLL IL. So this is root 3 VLL is V rated, because line to line voltage is V rated. And what is the line current in this in this side of the auto transformer? It is I starting line. So this is I starting line. And what about the VA rating on this side of the auto transformer, at the output of the auto transformer? Okay, so this is also root 3 times of, but V line to line is what? XV rated, because this is X times of V rated. Because of this tappings of the auto transformer, it becomes X times of V rated. And what is the line current here? Line current is this I starting line machine, which we have found here. Okay, so what happens to the starting current which is finally drawn from the voltage supply? So this is the current which we are interested in, okay, because this is the current which is getting finally drawn from the voltage supply. So you will see that the starting line current which is drawn finally from the supply becomes x square of factor of this DOL starting. So here you can see that previously from this reactor starting, we were able to reduce the line current by the factor of x, but here we are able to reduce it even further by x square. Okay, but here also you will see that the starting torque of the auto transformer also becomes x square of the DOL starting. Like here also it was x square, here also x square. But at least we are able to uh, reduce the starting current further. Okay, so here in this method, starting line current is x square of starting line current of DOL, and this starting auto transformer is x square of starting DOL. So both becomes reduced by x square. So earlier this reactor method, it was only x times. So I'll write here this reactor also. I starting reactor is only x times, okay, of I starting line DOL, and torque starting reactor is x square times of torque starting DOL. Okay, so this is for the reactor and this is for the auto transformer. So, but you can see that here we are losing in the what you say torque capability, right? Starting torque is also getting reduced. So now let us see the another method. Now in the other method, this is the star delta starting. Now, as I said in star delta starting, what happens is, first of all, this can only be applied if the motor under normal operation runs in star connection. Okay, so once this starting is method is done under normal operation, the machine should run in delta connection. That is the one thing. So what happens at this time, at the time of starting, what you do, you connect your stator of the induction machine in star connection. Okay, so you can have some switch arrangement which will help you to change from the star connection to delta connection. Okay, their switches can be possible. Okay, so in the starting, this is, let us say it is made in star connection. So what happens to the this phase this phase voltage? So phase voltage becomes 1 by root 3 times of the line voltage for star connection. So I starting line current is V rated by root 3 into ZSC. Okay, so this is the change. So what happens here? So this is the V rated by root 3 into ZSC. So and we have so you see here. So for the star connection, the line current. So I'm writing star is equal to phase current or winding current. So let us say this is winding current. And what is the winding current? So winding current is what? It is V phase. So this is R1 JX1 R2 dash by S equal to 1 and JX X2 dash. Okay. So this is V phase. And let us say this is ZSC. So what is I winding current? It is V phase by ZSC for the star connection. But what is V phase? We can see that V phase is rated voltage by root 3, right? So this is what V rated by root 3 into ZSC. So what happens to this line current? Because line current is equal to phase current for star connection. So it also becomes V rated by root 3 into ZSC. Okay. So this is what is happening. So starting current with the star connection becomes 1 by root 3 into V rated by ZSC. But what about the direct online starting? So for the direct online starting, we saw that it is root 3 times of V rated by ZSC. So if you take the ratio of the two, so you will see that the starting current by the star delta method is 1/3 of the starting current by the direct online starting method. Okay, and what about the torque? So you see so this was the starting torque in the DOL method. So see, the starting torque in the DOL method was 3 times of I starting winding square into R2 dash. So this is the starting torque in DOL method. So this is what we are writing here also again. Okay. Now what about the starting torque in this star delta method? So this you will see it will become what you say 1 by 3 times of starting torque of DOL. So here the starting torque becomes one third, but and also you will see that your even your this what you say this current starting current also becomes one third. Okay, so this is the star delta starting method. So this is what happens. So what happens is that there is some reduction in the starting torque in this method also, but it is somewhat less compared to here. It is like suppose you take so let us say you take x equal to so in basically it is similar to auto transformer method with x equal to 1 by root 3. Okay, you can check that. So this is what happens. So here in star delta this starting method, so you are not connecting some external auto transformer and you are not connecting some external reactor. Okay, what you are doing it with by changing only the machine connections, you are able to do it. Okay, so these are the four starting methods. Though there is no question in this in this assignment which is discussed, but I discussed this theory so that if suppose some theory question is there in your assignment, you can answer it. Okay, so till now in the starting method, is there any doubt in the four starting methods? Huh. Yes, because that is true, because but in direct online starting you're not doing anything, right? So it is the thing, it is the yes, it is like a reference where you're doing nothing. So if you do nothing and by doing something, what change you're observing, so that is why we are taking it as the reference. We are not doing anything, you're just connecting it directly. Yes, yes. These four methods are common for both squirrel cage and slip ring induction motor. Only this rotor resistance method is only applicable for the slip ring induction motor. Hmm. No, where we were connecting the external resistance, this external resistance which we were connecting in the rotor circuit, right? Because in the stator circuit you can do for both the machines, for squirrel cage also and slip ring also. But slip ring in the slip ring induction motor only you have this rotor terminals accessible. Okay, so that is one. Okay. So now we will see the some speed control methods. I'm just what you said discussing the introduction part of the speed control, but you will see that there will some further speed control lectures which are there. So, but in the questions it is not there. So I'm just discussing the speed control basic theory. Okay, then maybe next week I will go in more depth of the speed control method. Okay. So so if suppose we have seen so let us now do this. So you see the sir has drawn the torque slip characteristics, but if you will see the torque slip characteristics, he has drawn it in a reverse way, because till now whenever we were drawing the torque slip characteristics, we were drawing it like this. Okay, so we were drawing it like this, where we were saying that okay, this is the slip equal to 1 for starting. Okay, but at slip equal to 1, your speed was 0. Sir has just flipped it horizontally. So what you can see that the starting is drawn here. Okay, and the the end the what you say this, so this s equal to 0, slip equal to 0 with ns equal to nr is drawn here. Okay, this point. So it is basically flipped horizontally. That is all. Okay. So what sir is trying to say is, we have seen earlier that if suppose we connect the rotor resistance, okay, in the slip ring induction motor. So when we connect the rotor resistance, so what happens? So we have seen that your curve basically shifts to the this side, right? It shifts toward the right side. We have seen earlier that as you keep on increasing the R external, your this curve will shift in such a way that your maximum torque will shift, your starting torque will also become high. Okay, so you can see all this. Right. So you can see that it shifts towards the right. So because sir has drawn it in the reverse way, so for him, what is happening? It is shifting towards the left. It is just flipped horizontally. Okay, that is all. So you see what happens by varying this external resistance in the rotor circuit. So this is your, so let me draw the machine. So for slip ring induction machine, you have the stator, and then you have the rotor. Now, like earlier in the slip ring induction machine, we were connecting the external resistance for getting large starting torque. So, or reducing the current, starting current. So here we are connecting it so that we can do the speed control. Okay, so let me write, this is rotor, this is stator. So this R external is connected in the rotor circuit. So here you can see that so what happens is that we have seen that as we connect the R external, what happens? This torque slip characteristics shifts towards the right. So because sir has drawn it in a flipped way, so it is shifting towards the left. Now what happens that the full load torque, the slip at which you get the full load torque, it changes, right? So suppose the full load torque line is like this, like a constant torque characteristics. So, so what is happening? This full load torque is what you say intersecting with this torque slip characteristics earlier at this point. Now it is intersecting at this point. So this at this value, the slip value is different as well as the speed value is different, right? So what we are doing by basically changing this external resistance, we can change the value of speed at which we get the full load torque. Okay, so this is the speed control in the slip ring induction motor, one of the methods of doing it. Another method in both the machines, whether it is squirrel cage or slip ring induction motor, it can be by changing this rated voltage. So if you change this rated voltage, what happens? This, suppose you are reducing the supply voltage, right? Because you supply voltage, you can only reduce from the rated value to the less value, not make it higher, right? Otherwise the windings will get damaged. So you are reducing the rated value. So if you reduce the rated value, so what happens? The torque slip characteristic shrinks like this. So what is happening, that the slip at which you are getting this torque, let us say this torque, is changing, right? But it is changing very slightly compared to the previous method where you are having very wide range of speed control. Okay, so this voltage control method is applicable for both squirrel cage and slip ring induction motor, but this speed control method is of this rotor resistance by using rotor resistance is applicable for only slip ring induction machine. Okay, so this, in this way you can do the speed control. But generally in the today's machines we do not use this speed control method, because now the inverters have been developed and also inverter technology has advanced. So what we do is, but we do the speed control by using the inverter. So what you have that, so we know that what is the relation, what is this, what is this ns is 120 f by p, right? This synchronous speed. So if suppose by changing the frequency of this stator voltage supply, if you can vary the stator voltage supply frequency, you can change the synchronous speed only. Okay, so even though you do not change the slip, but if the synchronous speed value only changes by changing the frequency, then you can control the speed of the machine, right? You can vary it. So this is what is done. So here what you have is that in your you will see that this v by f control method, so this is known as v by f control. Okay, v by f speed control. This is generally used with the induction machine. Okay, so here what you have, that you have a rectifier, because this inverter needs a DC supply. So for giving the DC supply from the three-phase AC supply, you use a rectifier. Now, after this three-phase, so this DC supply is obtained, it is given to the three-phase inverter, and by controlling this three-phase inverter, the modulation index and the switching if you control it by using some control mechanisms, there are some control you can do it by varying the modulation index control signal which you are giving to the three-phase inverter reference, okay, reference signal. So by using that, what you can do is you can vary the voltage of the this three-phase AC output voltage as well as the frequency of this output voltage. So in generally in inverter, what you have a carrier. So you have a triangular carrier. So this is a triangular carrier. This I am telling extra, okay, just so you know that how it is done. And then you have a modulating signal. So let me just draw it even more. Okay. So this is the signal which you are given, and it will try to generate this blue signal by switching. Okay. So sorry. Now, what you can do is you can vary this you can doing the control by using the control algorithms in the and by switching the three-phase inverter using the gate drivers. What you can do is you can vary this what you say this modulating signal. Like suppose you want to increase the frequency. So if you want to increase the frequency, then you can and if you want to suppose increase the frequency and also increase the voltage, so what you can do is you can do something like this. Okay, so in this way you are changing the frequency of this signal. So this is so let us say this is modulating signal 2, and this is your modulating signal 1. The reference signal which you want to generate using this inverter. Okay, modulating signal 1. So, by using this three-phase inverter and by applying this voltage control methods and by changing the modulating signal accordingly, the kind of voltage magnitude and frequency which you want, so you can apply a variable voltage, variable frequency AC signal to the stator of the induction machine. Okay, so here another thing is that suppose you want to do the speed control. Let us say you want to reduce the speed. So let us say you have ns equal to 120 f by p. You want to reduce the speed means you want to reduce the frequency. Now what is the voltage expression? So you will see that the voltage expression of an AC machine is written like this. It is 4.44 k f phi into number of turns n1, where if you write the value of phi, so you will see that the phi is V rated by 4.44 f kWn1. So you will see that phi is proportional to V rated by f. Okay, so suppose you want to reduce the speed, and so for that you will reduce the frequency. So let us say you are trying to reduce the frequency, but what will happen is that in if you see the BH curve of the any machine, induction machine transformer, so what happens is that it has two regions. One is the linear region and the other region is the saturation region. So generally we operate it somewhere in this region. Okay, so this is the curve. So for this curve, you have some phi value. So this is B versus H or phi versus I also. Okay. Now what happens that I magnetizing? Now what happens that because your frequency has reduced, so phi will try to increase. So now we will try to move because phi has to increase, so now we will try to increase the phi, so we will move in this direction. But as you move in this direction, so for suppose your frequency is half and phi will try to become double. Let us say you want to reduce the speed by half. So suppose you have reduced the frequency by half, so your phi will try to become double. But in that case phi will become double in somewhere in saturation region, very long at somewhere at this maybe this area, because this is saturated, right? So for phi to become double, it will be somewhere very far on in the right hand side. But for that particular value of phi, double the value of phi, the kind of magnetizing current which will be drawn will be at least 10 to 20 times. Okay, so what happens that So this will, what you said, damage the windings again. So that is why when we want to reduce the frequency for reducing the synchronous speed, so what we do, we reduce the rated voltage also along with it, such that V by F is kept constant. Okay. So what we want to do is we want to keep V by F constant, such that phi is constant. That is why when you are varying the frequency of the supply, you also have to vary the voltage of the AC supply also. Okay. Otherwise this V by F will not be constant, and it may go, this phi may go to saturation region for the low speed cases, and it will draw huge current, damaging the machine. That is why, for to avoid that, you keep V by F constant. And that is why instead of naming it as F speed control, it is called as V by F speed control. Okay, V by F drive. So this is known as V by F induction motor drive, because V by F ratio is kept as constant. Okay, so is this clear now? If there is any doubt, you can ask. Then I'll go to the questions. Is there any doubt in these things? Okay, so now I'll discuss the questions. Okay, questions are very straightforward. You can say that they are a little bit repetitive. Okay, like from the last assignment, whatever questions which we are seeing, it is almost repetitive. Okay, so let us now see the questions, but you have to remember the things, that is all. Okay, so this question is very easy. They have given you the wound rotor induction motor. Wound rotor means slip ring only. Okay, so slip ring induction motor standstill parameters. Standstill parameters means at slip equal to 1, they have given you the data of the rotor resistance, rotor reactance. Okay, and then they are telling you to take that what is a simplified equivalent circuit diagram, where this R1, JX1 and JXM all are neglected. So what you are left with is, you are left with R2 dash and JX2. That is all. This is all you are left with. Okay, so this is your simplified circuit diagram, because we are neglecting the stator parameters, and we are also neglecting the magnetizing and all those things. Okay, so so now what we have to do is, we have to estimate the slip at which the maximum torque occurs. Very simple, right? Because see, this is R2 dash by S. Now, so what should be this? So let me just do, right, make it like this. Okay, um let me flip this. Okay, so this is JX2 and this is R2 dash by S. Now we are varying the S, means this load is variable. Now as per the Thevenin theorem, what should be the value of Z load such that the maximum power is transmitted or maximum torque is occurred? So so it is at Z load equal to Z Thevenin. So here also this R2 dash by S should be equal to X2, means S should be equal to R2 dash by X2, right, which is alpha, which we have also noted, what you say, denoted as alpha. So this is the value of slip at which the maximum torque occur. So what is the value of slip? It is just the ratio of this R2 and this X2. So this R2 by X2 will give you the value of slip, which is around 1.17%. Okay, it's a very simple question. Now we go to the next question. Now in this next question, what we have to do is, we have to estimate the per phase resistance required to be added to the rotor to get the maximum torque at starting. Okay, so they are saying that this alpha should be equal to 1. So this R2 dash plus R external by S should be equal to 1. S matlab X, sorry, because S, the slip value is only 1, right? So this is x2 dash. So this should be equal to 1. So so r2 dash plus r external should be equal to x2 dash. So what we have? We have r2 dash as 0.015 plus r external equal to x2 dash. So R external becomes 1.28 minus 0.015. So this is how much? This is 1.265 ohm. Okay, so this is the value of external resistance which you have to add. Now you see they are asking estimate the per phase resistance in milliohm. So milliohm means, that is why you have to read the question very properly. Okay, you will calculate and then you will see, okay, this is 1.265 and then you will enter the value, but your answer will be still wrong because you have to answer it in milliohm. So this should be what? This should be 1265 milliohm. This is the answer which you have to enter in milliohm. Okay, so is there any doubt in these two questions? This question 1 and question 2? Okay. Yes. So I'm going ahead. So now what you have to do is, now we have to calculate, estimate the minimum value of per phase resistance required to be added to get the 1/4 of the maximum torque at starting. Okay. So what we have to do, we have to get T start as 1/4 of maximum torque. Okay. So this is what you have to do. So what is this ratio? So this is T start by T max is 1 by 4. And in the last class, we have seen how to write this torque ratios in terms of this slips, right? So let me just open the last assignment. So this is how you write. Okay, so here if you go in one of the questions, you will see that the ratio of this T, because what you see. So you see the T max is K by 2, whereas the torque at any slip S is K into S alpha by S square plus alpha square. So I will write it again here so that it is clear. Okay. So T at slip equal to S is first of all K into S alpha by S square plus alpha square, and T max is K by 2. So T at slip S equal to 1 will be how much? T at slip S equal to 1 will be K alpha by 1 plus alpha square. Okay. So what you have to do, you have to take the ratio of the two. So T at slip S equal to 1 is T start. Okay, so T start by T max becomes K alpha by 1 plus alpha square divided by K by 2. This should be equal to 1 by 4. So K gets cancelled and 2 goes in the numerator. So it becomes 2 alpha by 1 plus alpha square equal to 1 by 4. So this is a quadratic equation in alpha which you have to solve. So this becomes 8 alpha equal to alpha square plus 1. So this is alpha square minus 8 alpha plus 1 equal to 0. So if you solve this, you will get alpha as two values. Okay, so let us just try to see what are those two values. So I'm just solving it in my calculator. You can do it using this minus b plus minus root b square minus 4ac by 2a. Okay, but to save time, I'm doing it in the calculator. So this is 1, this is minus 8, and this is 1. So one value of alpha is 0.127, and one value of alpha you see is coming such an absurd value, 7.872. This is a very absurd value, right? The slip cannot be like so high, such a high number than 1. First of all, your slip should not be negative. Your slip should not be higher than 1, or your slip should not be what you say. So let me just write these things so that you will know which value to avoid. Okay. So note, calculated slip should not be negative, should not be greater than 1. So should not be greater than 1, and your slip should not be greater than alpha. So these are the things which you have to ensure. Now, earlier we saw that the so now this is the value of alpha which so here you are getting this 0.127 and this is 7.872, which is very absurd. Okay, so we are taking 0.127. Now, in 0.1, if you take 0.127, so what is the value of the rotor resistance which is required? So how you can find this? So you know that this R2 dash plus R external by S, which is alpha, which is slip, which you have X, which you have calculated. So this is um so this is X2 and this is slip. Okay. So this is the value. So this is the value which you have calculated. So this is R external by X2, and this slip you have got it as 0.127. Okay. So R2 dash plus R external is 0.127 into X2, which is 1.28. So this you can multiply, you will get it like this. So what will be your R external? So R external will be 0.1625 minus R2 dash. Okay, so you will see it is 0.1475 ohm. But remember, this is in ohms, and they're again asking in milliohms. So this has to be 1, 2, 3. So this is what? 1, 2, 3, 147.5 milliohm. So in the earlier question, this was like this. Okay. So this is the value of external resistance which you are getting. Okay. So this was also a very simple question. You just have to remember again, these are repetitive, right? I said this will be, you will be seeing some things will be repeated. Okay. So this you have to remember. And by using this, you can solve for this. Now they're asking you that after the addition of the external resistance to get 1/4 of maximum torque, which is the previous question, find the ratio of new starting current by starting current of the original motor. So let us now see. So let us see the two equivalent circuits. Okay, one is the without R external, because they're asking the ratio of the starting current with and without this external resistance. Okay, without external resistance with R external. Okay, so here you had because this is a simplified circuit diagram, so I have neglected the stator impedances and magnetizing reactance. Okay, so this is R2 dash by S JX2. Slip is equal to 1 at starting because this is both at starting. Okay. And this is JX2. Now let us see what is the starting current in the two cases. Okay. So let us see the starting current in two cases. So this is I starting is V phase by root over of R2 dash square plus X2 square. And I starting here is V phase by, so I'm writing I starting R external by root over of R2 dash plus R external whole square plus X2 dash square. Okay, so let us take the ratio of the two starting currents. So this is I starting, new starting current, which is with the R external, and starting current of the original motor, which is without the R external. Okay, so this is what? This is V phase by root over of R2 dash plus R external square plus x2 square into I starting of the original motor. So this is, let us say, original. Okay. I starting original is this V phase by root over R2 dash square plus X2 square. No external resistance. So this is V phase by root over of R2 dash square plus X2 dash square. Okay. So these two will go. So you will be left with this. So you can put the value of R2 dash and X2 dash. So this is root over of R2 dash square plus X2 dash square. So R2 dash is 0.015 and X2 dash is 1.28. So root over of 0.015 square plus 1.28 square divided by root over of R2 dash plus R external square. So we have seen that R2 dash plus R external in the earlier example, it was how much? We calculated it as 0.1625. This is what we calculated, right? R2 dash plus R external. So R2 dash plus R external is 0.1625 square. So here it is written as 0.1625 square plus X2 dash is here also 1.28. So plus 1.28 square. So if you take the ratio of the two, you will get this value. Okay. So is this questions clear? These two questions which I discussed right now. So if there is any doubt at any point of time, please ask in between. Okay. So now coming back here. So these are like simple, it's just the repetition of the last assignment. Okay. Now we will see the some more questions. Hmm. Now this is the another set of data which is given. So here a three-phase induction motor running at 1% slip. So it is saying that runs at 1% slip at full load. Okay. Stator impedances, rotational losses, and no load current are negligible, means the simplified equivalent circuit. Now they are saying if the per phase rotor resistance is made 3.9 times of the original resistance by adding the external resistance. So what will be the new full load percentage slip? Now this is a very interesting question. Okay, very interesting. So I'll tell you why this is interesting. So they are saying that first of all, you have a torque slip characteristics like this. Okay. So this is torque, this is slip, and this is the full load slip. Let us say it is a maximum torque, but let me just say this is the full load torque, somewhere near the maximum torque. Okay. So let us say it is somewhere here. T full load. Okay. So now if suppose you add the external resistance, then what happens? So what happens is that your this torque slip characteristics, it shifts like this. Okay. By adding R external. Okay. But you will see that the value of this T max and this value of this T full load will remain the same. Okay, so this is T full load at slip 1. Now this is T full load at slip 2. T full load at slip 2. They're asking that if you have added the R external such that the this R external plus R2 has become 3.9 times of R2. Okay. So what happens to this full load slip? So they are saying what is this new full load slip? Okay. So let me just open one previous assignment question. Okay. Mm. So you see in the last class also, we saw one very familiar question. Okay. So they were saying that, okay, if suppose the rotor resistance is, external resistance is added such that the rotor resistance becomes 4.5 times the original value. So, what is the new full load slip in percentage? Exactly same question, just this value is changed. Okay. So, we calculated it by taking this full load by T max and all this we did. And we know how to do it. The T max is K by 2 and is T slip at full load is K into S alpha by S square plus alpha. And we were solving. But here there is no, remember in the previous question, they had given the information of T max. Okay. All the time. But in this today's question, they have not given, but we have seen something interesting. Okay, so we solved all this, and we saw that okay, the new full load slip is 0.14. And so you see the previous full load slip was some 3%. Okay, now you will see that the new full load slip will be the same 4.5 times of the previous or full load slip. Why? Because you see, as I said, when this shifting was happening, this shifting was happening in such a way that this whatever our external, whatever is the factor by which this rotor resistance has changed, by the same factor the slip also changes, which we have seen in the earlier class also. Okay, so in this class also what will happen, that the factor by which your, so I'm just writing, okay, so I'm just writing it as a note, the factor by which the rotor resistance changes by adding R external, so let me write it as external resistance. Okay, by adding external resistance by the same factor, full load slip. They could have also asked you for the maximum torque slip also. It happens for the maximum torque slip also, the same thing. Maximum torque slip changes. Because by we are moving by the same factor, right? So since we're moving by the same factor, that the slip at which the full load and maximum torque occurred, that will also shift by the same factor. That is why the new full load slip will be 3.9 times of the old full load slip. Okay, so what was the old full load slip? This we calculated. Okay, so Mm, so this is the case. Okay. So this was the old, so this is the maximum torque, and this is the T max is given. So where is this full load slip, in which question it is there? This is the maximum torque. This is the total gate. Okay. So have they given? Oh, okay, okay, sorry. So they have given in the question only. Okay. So they have given that this 1% slip at full load, because this is the new question. Okay. So they are saying that they are, so this was 1%. Okay. So this is 3 point times of 1% is 3.9%. Okay. So this is the new full load slip, because they gave this full load was earlier happening at 1% slip. Now the new full load slip will be the same factor, which is 3.9 times of the old full load slip. Okay. So this is the thing. Now they're asking that estimate the ratio of new full load rotor current to original full load rotor current. Okay. So let us now then see the two circuits. So um, original circuit. So in original circuit, there was no R external. Okay. Without R external. And this is the new circuit with R external. So here what you have, this is mm, JX1. So R2 dash by new full load. So this is slip. Okay, because this is not starting, right? This is at some slip, which is new full, this full load slip. And this is Jx2 dash. So your I full load is V rated by root over of R2 dash by S whole square plus X2 dash S whole square. Okay. Now what about in this new circuit? So I full load is V rated. Now remember this R2 dash by S plus R external is such that it is 4.5 times of R2 dash by S. This is what is given in the question, 4.5 or 3.9. This is 3.9, sorry. So this is 3.9. Okay. So they are saying that R external is added in such a way that the new per phase rotor resistance is made 3.9 times of the original value. So the original value was R2 dash by S. So R2 dash by S plus R external is such that it becomes 3.9 times of the original value. Okay. So this is 3.9 R2 dash by S whole square plus X2 dash S whole square. Okay. So let us take the ratio. So this is original. This is new. So I full load new by I full load original is what? So new is V rated by root over of 3.9 by S um, divided by I full load original. So this is V rated by root over of R2 dash by S whole square. Remember this is S new and this is S old. Okay, they're not the same slip, remember. Because the full load slip in both the cases is different, right? So now let us see what is the situation. So this is what? This becomes R2 dash by S old square plus X2 dash square divided by 3.9 times of R2 dash by S new square plus X2 dash square. Now you see, so S old is 1%. Okay, so this is, so S old, you will see this is 1%. Okay, and what about S new? S new is 3.9%. So S old is 1% and S new is 3.9%. So you just substitute here. So this becomes R2 dash by 1. I'm just writing it like that. Okay, you understand. Plus X2 dash square divided by this 3.9 R2 dash by 3.9 because S new in percentage is 3.9. If suppose you're writing here, you have to write it in factor. So the 1% means 0.01. Okay. And this 3.9% means 0.039. So I'm writing it in the factor so that there is no confusion. Plus x2 dash square. Now what happens? So this 3.9 divided by 0.039 also becomes 1 by 0.01. So this numerator and denominator are equal. So this ratio becomes equal to 1. Okay. Because this 3.9 here, so this 3.9 here and 0.039, this ratio also is 1 by 0.01. So this numerator and denominator becomes equal. So that is why this is equal to 1. Okay. Now we go to the next question. Now in this next question, what we have to do? We have to estimate the new full load rotor copper loss to original full load rotor copper loss. So these were the two circuits with us. So this is the original circuit. This is the new circuit with R external. So this is R2 dash by S, and this is X2 dash, and this is X2 dash, basically J. So J is also here. This is R2 dash by S plus R external, which is 3.9 times of R2 dash by S. Okay. Now we have to find the copper loss. So this is I full load original, and this is I full load new. So what is the copper loss? It is copper loss at full load is I full load square into the rotor resistance. This is the full load copper loss. So the new full load copper loss will be what? New full load copper loss will be IFL new square into new rotor resistance, which is 3.9 into R2 dash. Okay. And this is new full load copper loss. And what is old full load copper loss? It is I full load original square into whatever is the rotor resistance. Rotor resistance was here R2 dash. So this is the ratio of these two. So this is like 1. Let us say this is 2. So 1 by 2 is what? Because we saw the ratio of the full load current new and full load current original is 1. So this ratio, the ratio of the squares will also be 1. So this will be 1 into 3.9 R2 dash by R2 dash, which is 3.9. So this becomes 3.9. Okay, this is the ratio. So is there any doubt till now? Okay. So if there is any doubt, please ask. These questions are easy only. Just have to know how to apply things. Okay. Just have to know how to solve it, but by solving is very easy, these questions. So now what you have to do, you have to estimate the ratio of new full load output power to original full load output power. Now what is the output power? So here you see, so we know what is our this power flow, right? So we have air gap power, and from air gap power you take out the rotor copper loss. So you have the gross mechanical power. Okay. Because there is nothing mentioned about the friction, so you say that friction, you see they have mentioned rotational losses are negligible, means friction losses are negligible. So they are saying that this gross mechanical output power is equal to your shaft power. This is your final output power. Okay. So this is your final output power. And you see here what we have is this air gap power minus rotor copper loss. Okay. This is equal to output power. Now what is air gap power? Air gap power is what? This is 3 I2 dash square R2 dash by S minus 3 I2 dash square R2 dash. Okay. This is equal to output power. So output power, okay, is, you will see that it is equal to, so let me just move it here. So it is equal to air gap power into 1 minus slip. Okay. So that is the thing. So this is the thing, because this is, if suppose this is air gap power, so we are saying that this is air gap power. So what is rotor copper loss in terms of air gap power? So if suppose air gap power is 3 I2 dash square R2 dash by S, and rotor copper loss is 3 I2 dash square R2 dash. So in terms of air gap power, rotor copper loss is what? Air gap power into slip. So this is slip into air gap power. So from here I am writing this. Okay, that output power is equal to air gap power into 1 minus slip. So this is the thing which you have to remember. Now, what is the air gap power? So air gap power, as I said, is 3 I2 dash square into R2 dash by S. So this is, so what we have to do. So the ratio of the two will be what? So it will be ratio of 3 times of new full load output power, means I full load new square into this uh, R2 dash plus R external, because now in the circuit there is, in the new circuit after adding the resistance, it is R2 dash plus R external by S new. Okay. In, so this is air gap power. This is air gap power new into 1 minus slip new. Air gap power into 1 minus slip new will give me the output power, new output power, full load output power. So this is 1 minus S new. This divided by the air gap old into 1 minus S old. So air gap old is 3 into I full load old square into R2 dash by S old, because in the earlier circuit it is R2 dash only, into 1 minus S old. In the original circuit only R2 dash is there, but in the new circuit it is R2 dash plus R external. So you see 3 gets cancelled. So this can be written like this. It becomes new full load current, full load rotor current square, IFL new square, divided by original full load current square. So original full load rotor current square, this is I full load old square. Okay. Into so here this is R2 dash plus R external by S new. Now what is this R2 dash plus R external? So R2 dash plus R external is 3.9 times, because in the question it is said that R2 dash plus R external is 3.9 times of R2 dash. So this is what we are doing. We are writing it as 3.9 into R2 dash by S new. So S new we have seen it is 3.9%. We have seen that. We have seen that it is 3.9% here in this. Okay. Full load torque, full load slip. So here, so this is, so here in R2 dash plus R external, you're writing 3.9 R2 dash. So you have written 3.9 R2 dash here. Okay, this is very small, I guess. So I think you may not be able to see. So let me just increase the size of this. Okay. I think visibility will be low. Okay, I think now it is good. So here you see this is, so R2 dash plus R external is 3.9 R2. And what was this new slip? It was 3.9 times of the old slip, which is 3.9%. Old slip was 1%. This is divided by 0.039 into 1 minus S new. 1 minus S new is 1 minus new slip, which is 0.039. Divided by original full load current, because I full load old. So I full load old is original full load current square, into R2 dash by S old. So this is R2 dash, and old slip was 1%. So this is R2 dash by 1 into 1 minus S old. So this is 1 minus S old. So this ratio of the current is 1. So this cancels out. And here you can, and you will see that this 3.9 R2 by 0.039 and R2 by 0.01, there also cancels out, because 3.9 by 0.039 is 1 by 0.01. So this also gets cancelled out. What you're left with, only 1 minus new slip divided by 1 minus old slip, full load slip. So in this way you will get 0.97%. So is there any doubt in this question? Because in this question we did many things. We applied this power flow diagram also. Then we applied the previous questions, whatever we obtained in the previous questions for this data, we use that information also. So is there any confusion anywhere in this question? Okay. So Shiv Kumar Mahato, is it is clear to you? Is if there is any doubt, please ask. Okay. Okay, okay. So if it is a question, then you ask. Okay. Now we are seeing the another set of questions. So here they have, it's this question is very easy. Okay, this question you have done it so many times. Okay, so they are saying that consider a three-phase induction motor with negligible stator impedances, rotational losses, and no load current. So here they are telling you to take the simplified equivalent circuit diagram. So the ratio of the maximum torque to full load torque is 5, and the ratio of maximum torque to starting torque is 2.5. So they are asking estimate the slip in percentage at which the maximum torque occurs. So here, so which ratio you will take, right? The ratio of maximum torque is available to full load torque also, and the ratio of maximum torque is available with the starting torque. But if we have to solve for the slip at which maximum torque occurs, basically alpha, so what we need to know, we need to know the slip of either of the two things. So full load slip is not given to us. Full load slip is not given in the question, so we cannot use this ratio. The starting slip, we already know that starting slip is equal to 1. So we will be using this in this ratio for solving this, for getting the maximum torque slip. Okay. So we know that the maximum torque T max is equal to K by 2, and T start. So let us say T at any slip equal to S. So let us say torque at any slip equal to S. Okay. Is what? It is S alpha by S square plus alpha square. So T at slip equal to 1, starting torque will be what? Alpha by 1 plus alpha square. So if we take the ratio of the two, so let us say we are taking the ratio of T max by T slip 1. So it is what? So this is okay. So what you can do is you can maybe take the other ratio, because other ratio will give you something which you are seeing continuously. Okay. So let us say this is T at slip S equal to 1 by T max. So this will give you 2 alpha by 1 plus alpha square. Okay. But in the question, what is given? It is given that the ratio of maximum torque to starting torque is 2.5. So the ratio of starting torque to maximum torque will be 1 by 2.5, because it is just inverse. Here what we have written is inverse of this ratio. Okay. So this is the thing. So here what you will get is you will get a quadratic equation. So it will be 1 plus alpha square minus 5 alpha equal to 0. This is alpha square minus 5 alpha plus 1 equal to 0. So you see, you solve for alpha, you are getting this one value as 4.7912 and another value is 0.208. So you can see that this, as I said, alpha has to be less than 1, but this is not less than 1, so we have to neglect this value. So this is the right value. So this is the slip at which maximum torque occurs. Okay, into 100% will give you slip in percentage. So this is the slip at which maximum torque occurs. Okay. Now they are asking for the same data, what you do, you have to estimate the full load slip. So we will now use this information. Okay, because now we know the maximum torque slip, so we can find the full load torque slip. So what is the TE at any slip equal to S? So this is S alpha by S square plus alpha square. Okay, and what is T max? T max, T max, right? T max is what you say, this is K by 2 and this is Ks alpha by S square plus alpha. So T by T max 2s alpha by s square plus alpha. Okay. So this becomes 2s alpha by s square plus alpha. And this ratio is given to us in a reverse way. They have given maximum torque to full load torque, but we are taking it as what you say reverse, right? Full load by maximum. So this has to be 1 by 5. Now, so here what we get, you get it like this. Okay. So first of all, we know what is the this. So the slip at which maximum torque occurs, so slip at which maximum torque occurs is also equal to alpha equal to R2 by X2. Okay, so this value 0.208 is equal to alpha. Okay, so this alpha we already know from the previous question, which is the slip of at maximum torque, or R2 dash by X2 dash. So this is how much? 0.208. Okay. So in this equation, we have to solve for s. So what we have? So you have s square plus alpha square minus 10s alpha. So this becomes, so I'm writing directly. So this becomes minus 2.08 alpha. Sorry, s. Okay. So because alpha I'm substituting. Okay. S plus 0.208 square. Okay. So this is 0.208 square equal to 0. So what is the value of S? So I'll tell you. Okay, so this is 1. This is minus 2.08 and this is 0.208 square. So you have S equal to 0.021 and how much? Oh, sorry, I did. Actually, I pressed clear in my calculator on 2.08 and this is 0.208 square. Okay. So one is 0.021 and the other one is 2.058. Again, this value is greater than 1. So we will not take this value. We will take this S equal to 0.021. So you will see this is the answer 0.02108. Okay. So this is the answer. This was also simple. Now we will see the last question. Now in this last question, they are saying that estimate the required percentage reduction in the rotor resistance to bring down the full load slip to 1%. Okay, so how to do this? Let us see. So assuming that the load torque is unchanged. So first of all, what is this? So we know that this, so here it is like this. So you can do it in two ways. Okay, so first way is that we know that the percentage, so the percentage, so first of all you see this R2 nu is equal to um, alpha nu by alpha old. Okay, so what they're trying to say here, so this is okay, I understand. So the ratio of this new full load slip to old full load slip. Okay, so they are saying like that. Okay, I understand. So first of all you see, uh, so what is, so we know that the in the torque slip characteristics. Okay, so we have seen that by changing the R external, whatever by the whatever factor you change the R external, the value of the full load torque slips also changes in the same ratio, right? So let us say these are the two values. So this is the ratio. Okay, so they are saying that this is basically S new and S old. So they are saying that the factor by which your rotor resistance change is the factor by which your slip changes. We have seen that, right? When we changed the rotor resistance by adding the R external, so it also, the slip also changes. Okay. And the factor is also the same. Factor remains the same. Okay. So this is the ratio. So now they are saying that the, first of all, our old full load slip was what? Our old full load slip. So this old full load slip was what? 2.108%. So this is 2.108%. Now they are saying you have to bring down the full load slip to 1%. So this is now 1%. So they are saying new slip should be reduced. So they are saying that, okay, you have to reduce the rotor resistance so that your curve shifts like this. Okay. So they are asking you that, so let us say this is 1%, and they are saying that this was 2.108%. Okay. So they're saying that how much the rotor resistance has to be reduced, because we know that if the slip has to reduce, then rotor resistance has to reduce. So by what factor the rotor resistance has to reduce such that the slip reduced from 2.108% to 1%. Okay. So this will be the ratio. So now what you can do is, because we have to express the change in the terms of percentage, right? So what is the change in percentage change in resistance? So percentage change will be what? It will be R2 new minus R2 old by R2 old into 100%. This is how we express the change in percentage, right? So what is our R2 new? It is proportional to S new. So this is 1 minus R2 old, which is proportional to S old, which is 2.108. And what is our R2 old? Proportional to S old, which is 2.108 into 100%. So you will see that the change is minus 52.57%. Minus means we are reducing. Okay. So this is how you can solve this question. So this is the last question of this assignment. Is there any doubt anywhere? These questions are simple only. Okay. So is there any doubt anywhere? Okay. Okay. So they're asking you regarding the ratio of the starting torques, right? So how you can do it? So first of all, you can do it like this, that starting torque new by starting torque old, right? So you see the starting torque is proportional to 3 I2 dash square into R2 dash by S. Okay. This is R2 dash new, and this is 3 I2 dash square R2 dash old by S, and this is I2 dash new and I2 dash old. Now, so I'll just discuss it in the new slide. Maybe that is better. Okay. So this is starting torque new by starting torque old. So this is what? It is proportional to the output power. And what is the output power? Output power, if suppose you neglect the rotational losses, it is proportional to what? So it is proportional to the output so the to this gross mechanical power, which is nothing but air gap power into 1 minus slip new. This is air gap new by air gap power old into 1 minus slip old. Now, what is this air gap power new? It is 3 I2 dash new square into R2 dash new by S new. into 1 minus S nu divided by 3 I2 dash old square into R2 dash old by S old by 1 minus S old. Now you know the value of the old slip, you know the value of old slip, you know the value of new slip. Also, you know the ratio of R2 new is to R2 old by this relation. So here you know the ratio of R2 new is to R2 old, you know the ratio of S new is to S old. You also know these things. Okay. Now here in the current, what you have to do is you have to solve for the current. Now what will be I2 old and I2 new? So let us see that. Mm, so, so let us say this is I2 old. So I2 old will be V by root over of R2 old square plus x2 square, and I2 new will be v by root over of R2 new plus x2 square. Right. So instead of again I2 old and I2 new, you substitute the value and then you will also find it in the ratio of R2 old is to R2 new. Okay. So if you do that, you can find the ratios here. So you have to, so you know the ratio of R2 new is to R2 old, you know the value of S new and S old, okay, and you also you can express this I2 old and I2 new as the ratio of R2 old is to R2 new. Okay, so if you do that, you can get this ratio. Huh. Okay. So so that is it. So if you have eighth question, eight. Hmm. Yes, it is exact similar, correct. Hmm. But here what happened that full load current and new full load current, the value was same. But here this R2 dash is now changed. Okay. Now the this is not the same way. Okay. So here, so you just see, okay, I forgot one thing. It's good that you went to that question. Okay. So this is basically R2 old by S old. So this is R2 old by S old whole square. Okay. This is what I forgot. Oh, it is not going. Okay, so this is R2 old by S old whole square, and this is R2 new by S new. So this is R2 new by S new whole square. Okay. Now it will be very easy. It will be simpler for you to solve. Okay, because you see this R2 new, so R2 new by S new is equal to R2 old by S old. So R2 old by S old and R2 new by S new. So you will see that this I2 new square and I2 old square will cancel out, you know. So in this case also you see this. So basically you see R2 old by R new is equal to S old by S new. So R2 old by S old is equal to R2 new by S new. So you will see that this I2 old and I2 new will cancel out. 3 cancels out. R2 old by, as I said, R2 new by S new and R2 old by S old cancels out. So what you are left with 1 minus S new by 1 minus S old. Okay. Is it okay? Ha. Ha ha. Hmm. Okay, 0.021. Ha ha. Yes, 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 yes. You found the full load slip percent, full load. Hmm. No, see, alpha is the value which is the see. So alpha is what? Alpha is the slip at maximum torque or R2 dash by X2 dash. So alpha at maximum slip at maximum torque we have 20.87. So alpha is 0. No, I just put alpha in this equation. This equation I just substituted the value of alpha. Mm. Mm. हाँ. Yes, yes, you can ask. Okay. Okay, then, so that is it. So if you have other questions, you can ask. Okay. Okay, Shiv Kumar Mahato is saying something. Thank you for your praise. Okay. So if you have any doubt, you can ask. Okay. Okay, then. Ha. Okay. Okay, then. Okay, then I'm stopping the class today here. Thank you, everyone. I'm leaving. Okay. You can also leave if you have no other questions. Okay. Okay, then Shiv Kumar Mahato. You can leave.